Hello and welcome to this part of the lecture. We will now start looking at coordinate rings of algebraic sets. And that means that we will look at rings of functions defined on algebraic sets in some way. Regular functions, whatever that means. So let's define what it means. So you take an algebraic set in a to the power n in the affine space, and we will call a polynomial function, or as sometimes it's called in the literature, a regular function on X. It's a map from X to the field K that is given by some polynomial, meaning that there exists a polynomial so that phi of x is equal to f of x for all x in X. So it's the restriction of some polynomial function to this algebraic set. Now recall that two such functions, by the last remark of the previous video, two such functions will be equal on X if and only if they coincide modulo the vanishing ideal of X. So functions are not given by the polynomial ring as a whole, but a more apt object is the polynomial ring factored by the vanishing ideal. So this is what we call the coordinate ring of X, and it is the commutative unital K-algebra. The definition of K-algebra comes in a moment, given by taking the quotient ring of K T1 to Tn by this ideal. So this is precisely polynomials modulo the equivalence relation that two polynomials are equal if they vanish everywhere on X. And here a K-algebra is a ring that also has a K-action. So it's a K-vector space where the ring multiplication is bilinear. That is what is meant by a K-algebra. And this is certainly the case here. The multiplication of polynomials is K-bilinear. So that is the coordinate ring of an algebraic set. Let's look at some examples. So the coordinate ring of the whole space, this is the whole polynomial ring. Why? Because we have seen that the vanishing ideal of this is the zero ideal, so we would be quotienting by the zero ideal, and this wouldn't make any difference at all. Two polynomials are equal if and only if they're equal modulo 0, hence they are equal. The coordinate ring of a point is isomorphic to the field itself. Why is that? Well, so we have this is by definition K T1 through Tn modulo the vanishing ideal of a point, and so this is a maximal ideal. And from this fact of from algebra that we use to prove the weak Nullstellensatz, we know that this is a finite field extension of K, but since K is algebraically closed, this is isomorphic to K. If we have a line, then the coordinate ring of a line is the polynomial ring in one variable. So this is because, let's take for example in K T1 T2 the line T2 equals a T1 plus B. Then quotienting, so the line is given by this equation. So quotienting by this ideal, this is simply the polynomial ring in T1 and a T1 plus B, but this thing is already there because it is already in the polynomial ring of T1, so this is the polynomial ring in T1. So this line is parametrized by T1 if you wish. So one question to ask is, okay, which K-algebras And as with rings, when we say k-algebras, we always talk about unit or commutative k-algebras. So which k-algebras can arise as these O of x for an algebraic set X? Well, remember, this is just saying that which k-algebras can arise in this fashion. And so it's basically a question of what the restriction on this ideal, being the vanishing ideal of some set, is. And to characterize these algebras, we need two words. So a k-algebra is called affine if it is finitely generated as a k-algebra. So it has a finite set of generators. And so it is the commutative algebra generated by these generators modulo some relations. Or in other words, it is the quotient of some ring in finitely many, some polynomial ring in finitely many variables by some ideal. Second, a ring is called reduced if it has no non-zero nilpotent elements. Nilpotent elements are elements x such that x to the power n is equal to 0. So the ring might still have 0 divisors. We might still have some different xy equal to 0, but we exclude the existence of nilpotents. This is equivalent to saying that the radical of the 0 ideal is the 0 ideal. That's exactly the definition. And then it is not hard to prove that a k-algebra is isomorphic to such a coordinate algebra or a coordinate ring, if and only if it is affine and reduced. So affine means that it is of this form, and reduced means that the 0 ideal in this quotient ring is its own radical. And so this means that the ideal J is its own radical in the ring Kt1 to Tn. And that was precisely the condition on the, that was ideals that are not radical cannot arise as the 0 ideals or the vanishing ideals of algebraic sets. This was the content of the previous part of the lecture. Now, with this, we have taken a step, namely the following. Previously, we only had the polynomial ring, namely the coordinate ring of the whole space. And so our algebraic subsets, or our algebraic sets, had to be viewed as subsets of this huge space. We had to go back and reference to the whole polynomial ring every time we wanted to do something algebraic. But now we have defined coordinate rings, and so we can do things relative to some algebraic set. So we can take an algebraic set X and consider that as our universe instead of AN. Namely, we define algebraic subsets. So if we have a set of now functions on X, or regular functions on X, then the vanishing set, or the 0 locus of this, is defined exactly in an analogous manner as the set of all X in X, where all these functions vanish. And subsets of this form are called algebraic subsets of X. If you read in Gatman, he already calls them affine subvarieties, because he calls algebraic sets already affine varieties. And then, as before, we can make the analogy of the ideal of an algebraic set. So this can be defined for any subset of X, algebraic or not. We define the ideal of Z to be all the functions on X that vanish on all points in Z. And one can prove that this is a radical ideal in the algebra of regular functions in the coordinate ring. And then we also have the relative Nullstellensatz. So this is precisely the statement of the Nullstellensatz upon replacing the vanishing set and the vanishing ideal with these relative versions, the vanishing set relative to x and the vanishing ideal relative to x. And it says the same, so if you take them in one order, you get the set back. If you take them in the other order, you get the radical of the ideal. And so you get inclusion, sorry, not preserving, but reversing bijections between algebraic subsets of X and radical ideals of O of X. Moreover, the coordinate ring of Z is the quotient of the coordinate ring of X by the relative vanishing ideal of Z. You can deduce this algebraically because this is the coordinate ring of the affine space quotient I of X, and look closer at the relations of the ideals and so on. So this gives us a relative version of everything, and of course there's another way to view it. You can still view it globally. So an algebraic subset of X is just going to be an algebraic set that is contained inside X. So you can view everything with respect to the whole ambient space, but this makes the theory more flexible. And indeed, let us end this lecture by looking at some philosophical aspects. So far we've studied algebraic sets sitting inside a to the power n. And the embedding makes this study extrinsic. So we don't have an intrinsic study of these algebraic sets. True, we can view them as subsets of other algebraic sets, but still there is something greater than some embedding that we always need to take care of. Thanks to the Nullstellensatz, the coordinate ring contains a precise description of the structure of how this X is embedded into the ambient space. So our way to move away from this embedding dependent version of algebraic geometry will be to study algebraic sets as pairs of some space X, not embedded in anything, just some abstract space, together with some algebra of functions defined on this. And if we want to study more than just algebraic sets, this formalism lends itself to it by allowing us to generalize this thing by replacing the one ring O of X with a whole bunch of rings. But this comes later. And so the first thing to do is to define what it means to be a space. We need some sort of structure. X cannot be just a random set, because we want to do things like closed subsets and so on. And so we need an intrinsic geometric structure on X, and that is a topology. And this will be what we will deal with the next time. And this concludes today's lecture.